We are live. Awesome. Well, welcome everybody today. We are very excited to have Singwen Gao presenting their AI Stats 2022 paper, Provable Lifelong Learning of Representations. She's a PhD student in machine learning at Georgia Tech, just like me, and we are very excited to hear you talk today. I think bringing a theoretical aspect to continual lifelong learning is something that many of us may be afraid of, but we deeply yearn for an expansion of this topic. So I guess without further ado, please take it away.
Sure, thank you. Hello, everyone. I'm Xian Tao from Georgia Tech. So today I will talk about my recent work, Provable Lifelong Learning of Representations. And this is the joint work with Weiyang Liu and Santosh Vanpala. So today my outline will be like 4 parts: the background, the settings and algorithms, the sample complexity analysis, and the experiments. So first, let's talk about the background. I know like our audience is an expert here. So lifelong learning is introduced from the How Human Learns. So we can see like different objects from since we're born, and our brain could extract features from those objects. For example, the ear shape, the eye colors, and when we see a new class, for example, in a sheep, we can use the current features we have learned from our brain to learn this new class. Or we can learn more new features when we see new classes. So lifelong learning is also called continual learning and incremental learning. There, the tasks to be learned arrive sequentially over time in arbitrary order. And while learning, the knowledge from previous tasks can be captured and transferred to the subsequent ones to improve the efficiency. So here, we usually have assumption that all of the tasks share a set of common features. So we can have a lot of tasks, but like the common features number is much less than the number of the tasks. So this is actually similar to the transfer learning, but like for the multitask learning, we usually extract features from the source tasks and then fine tune them to the target task, while we do not care about like how this fine-tuned features work on the previous tasks. But in lifelong learning, we need to keep all of the tasks we have met and keep them to be high accuracy. So in lifelong learning, there is one very critical problem named catastrophic forgetting. So the performance on the old task will drop dramatically after learning a new class. So this can be caused by because we are learning on non-IID distributions and the tasks are encountered sequentially, and especially when we use the backpropagation, like this would increase this phenomenon. So there are usually 3 main approaches to solve the catastrophic forgetting. The first one is to add a regularization term. For example, we can use the knowledge distillation to penalize the changes of the parameter so as to let the performance of the previous task not decrease so much. And the second way is to freeze the networks from the previous tasks and adding branches to the new tasks. So this can easily handle the catastrophic forgetting, but the problem of this method is that it might incur a high model size as the number of the tasks get larger. The third way is to replace the previous task exemplars. So we can like store some of the data from the previous tasks and to make sure that the previous task performance does not drop that much. So our algorithm is actually based on the second approach here. So we dynamically change the network architecture, and we solve this problem of the high model size because we have upper bound our size of model. Cool. So now let's talk about the settings and algorithm. Because this work is mainly on theoretical side, so what we consider here is a very simple setting of the task incremental binary classification. So we let X to be the input space in Z dimension and Y to be the label space, which is a binary space. We consider M tasks in total, so they come in a stream. For each sample XY from the task I, it satisfies that it is labeled as sign of AI transpose X. So here we assume that all of the tasks share the common feature sigma X, which is W transpose X. And the number of the common features K is much less than the input dimension Z and the number of the task M. So our goal is to learn each task sequentially such that the maximal error of all of the tasks is smaller than the target error epsilon. And the error of the task I is defined here by the predicted label is not equal to the true label under the distribution of our input data. And we will generalize it to the nonlinear features by adding some nonlinear activation of the features, like sigma of W transpose X and later. So here is a sketch for input dimension is 3, and we have 3 tasks, and they share 2 common features. So we can see that after learning the 2 features, we can efficiently learn the 3rd task. And this could be more beneficial when we have more and more tasks. So here is the benefits of learning the features. Because the number of the data sample we need is dependent on the input dimension. So for an input dimension Z, if we want to solve the binary classification up to error epsilon, we need big O of D over epsilon samples. But if we can learn the features, which number is K, we can just use big O of K over epsilon to learn a new task accurately. So lifelong learning here can help improve the sample complexity. Okay, so we have only one assumption in our paper, which is about the data distribution. So as a warm-up, our assumption is based on the low concave distribution, where the density is a low concave function. So the low concave distribution is a very broad distribution class, which contains a lot of common distributions like normal distribution, uniform distribution, gamma distribution, and beta distribution. So our assumption is actually defined here. So let theta to be the angle between 2 vectors. We assume that there exists universal constant C2 and C1, such that for any unit vectors U and V in Z dimension, the testing error of the binary testing error is in the same order with the angle between them. So our assumption is proved to be satisfied by all of the low concave distributions. So actually our assumption is weaker than the low concave distributions. And also, as we can see in this definition, our assumption helps us to connect the test error to the distance matrix. So this enables us to use the proof techniques from the geometric side. Now I will introduce our 2 algorithms here. The first one is the basic lifelong learning algorithm. So our algorithm maintains a set of features sigma along training. As when a new task arrives, we attempt to learn the new task with the current features and check whether we can have an hypothesis with error less than epsilon. So if yes, as the case 1 in this plot, we can just record the linear combination parameters and we are good for this new task. And we can move on to the next one. Otherwise, if we have a large error, which is the case 2 here, we need to learn a new set of features to solve the current task up to error epsilon accurate. and then add all of the new features to the feature set we are keeping. So here, the epsilon accurate is a number smaller than epsilon, because if we make learn each new task just up to arrow epsilon, then in the end we will have a larger arrow. So as the remarks here, we avoid catastrophic forgetting by freezing the old task classifier. And we will prove later that the number of the tasks to learn new features is bounded. So each time we learn a new feature, as I mentioned, we need to learn up to a smaller arrow epsilon accurate, because the arrow of each vector will accumulate in their span. And in the end, we hope that the final feature subspace that we have learned is up to desired arrow epsilon. And in our algorithm, we actually use this epsilon accurate as epsilon over constant times square root of k, where k is the number of the features. And this is our second algorithm, which is called lifelong learning with representation refinement. So we basically adopt the same strategy as the basic lifelong learning algorithm, but whenever we learn the new features, we do a step of the representation refinement on all of the features we have learned. So basically, our representation refinement step is to find an approximated feature subspace with the minimal dimension. And we can write it as an optimization problem here, which is to minimize the dimension of V such that the distance from each feature we have learned, Wi tilde, to the target subspace V is more than epsilon accurate. But this problem is actually NP hard, and we cannot solve it efficiently. So in the linear case, we provide an efficient approximation algorithm for it by using the STP relaxation and the PCA. So the theorem for our approximation algorithm is stated as here. So for our original NP hard representation refinement optimization problem, if there exists a subspace V star of k dimension and the distance from each feature we have learned to the subspace V star is smaller than epsilon accurate, then our approximation algorithm will output a 2k minus 1 dimensional subspace solution with approximation factor square root of 2 in maximal dimension, which means that the distance from each learned features to our output subspace is smaller than square root 2 times epsilon accurate. So like the existence of the subspace is assumed by our setting. So this shows that we have an efficient algorithm to do the representation refinement step with the constant approximation. So the analysis of this part is just an STP relaxation. And in our right-hand side, the variable x represents the square of the projection matrix to V complement. And yeah, this is basically like why it works. Cool. So then we will move on our main contributions on the sample complexity analysis. So we first revisit the setting, which is the task incremental binary classification of the input dimension V, and output is a binary. We have m tasks, and all of the tasks share a k common features. So we have the main theorems of our two algorithms. So as I mentioned, the epsilon accurate is epsilon over square root of k, and we have shown that the total sample complexity to learn all m tasks within arrow epsilon is O tilde of d times k to the 1.5 over epsilon plus km over epsilon. So this bound has two terms. the first terms comes from learning the task that we learn new features, which is the case 2 in our algorithm. And the second term is the samples from the task that we do not need to learn new features. Because we have shown that in the end, our number of features we learned is O tilde of k. So the second term is actually just learning from this k features, and we have m tasks, so it's km over epsilon. And for the first term, because we need to learn new features, so everything is started from scratch, which is in d dimension, and we need to learn it up to arrow epsilon accurate. So we have another square root k term, so it's dk to the 1.5 over epsilon. So we compare our results with the multitask learning and lifelong learning work recently, and we can see that our result has the best dependence on the feature dimension k and the target arrow epsilon compared to other works. And we have also done some simulations on this linear task incremental binary classification, and it shows that our two algorithms are performing well. Yes, so now I will talk about our proof intuition. So our proof is basically from the geometric way, and we can see in this plot. So let's V star to be the true feature subspace, and Vi minus 1 is the feature subspace that we have learned till to the step I minus 1. So in the I step, if we find that the target AI has a high accuracy using our current feature subspace Vi minus 1. So in this plot, we can see that the distance from this AI to the Vi minus 1 is larger than some constant times epsilon. Then we will learn a new feature that is close to this target's AI, which means that its arrow is smaller than epsilon accurate. Then our new feature subspace is the span of the original subspace and the new feature subspace. So it can plot it simplified by this Vi, and we can see that the learning this new feature AI will push our original feature subspace Vi minus 1 towards the true feature subspace V star. So if we can quantify the improvement in the angle between the learned subspace and the true subspace, then we can upper bound the number of the steps to learn the new features. So firstly, our data distribution assumption could transfer the testing arrow to the angle between the vectors. And we aim to find a feature subspace that is close to the true subspace, which means that they will have small angles between them. So here we consider the set of all candidate subspace, which means the subspace that is close to each learned features. If we denote I1 to I tilde k as the indices of the task that we learn new features, which is the case 2 tasks, then at the step ik hat, we construct a set of yik hat of all of the possible subspace V that are the feasible solution to our refinement optimization problem. So because our proof is, the intuition of our proof is from our refinement step, so this set yik hat is actually all of the candidate subspace up till the step right now. And we can say that because we are learning more and more features, so this optimization, we have more and more constraints. So the set yik hat is shrinking during the training. But we cannot quite easy to calculate how that set yik hat shrinks. So instead, we consider the set of the vectors that are well approximated by the current learned subspace. And we can quantify the growth of this set and prove our results. So technically, we let xik to be the set of the vectors in the unit ball in the k-dimensional subspace that are within distance epsilon over square root of k to all of the subspace in yik hat. So we can show that this set xik is a symmetric convex set, and the volume of xik is increasing exponentially. So finally, it ends up with covering a ball in the true feature subspace, and that this means that we can solve every new tasks because we have basically learned the true feature subspace. Yes, so to show that the set xik is exponential, the volume of it is exponentially growing. The key lemma here is to consider the max ellipsoid of the symmetric convex body. So the convex hull of this convex body with a unit vector will have like a constant increase in the volume. So this is because like each time we are adding a new feature, which is actually a unit vector. And we know that xik is a convex set, so our new xik plus 1 should be the convex hull of the original xik and the unit vector of the features that we have just learned. So this volume is increasing by a constant. So the termination is that our set of xik is covered in the unit ball. So this can upper bound the volume of it. And it also covers a small ball of radius 1 over square root of k. So this shows that any target function will have O epsilon arrow with the final representation. And because we have already shown that the increasing of the volume is by a constant, so we can upper bound the number of the steps to learn the new features, which is the number of the tasks that in case 2. So we can upper bound the total sample complexity. So previous result is about the upper bound of our algorithm, and we have also proved a theorem on the lower bound. So we suppose that a lifelong learner has the black box access to a single task learner that takes an arrow parameter epsilon as input and is allowed to return any vector that is within distance epsilon of the true target unit vector. So we can show that the lower bound of the total number of the samples need to learn all m tasks up to arrow epsilon is omega dk to the 1.5 over epsilon plus km over epsilon. This shows that our algorithm analysis is nearly tight. And the lower bound intuition is actually to finding the hardest case. So we can see this simple case when in 3 dimensions and the number of features 2. So our algorithm returns the features where the arrow concentrates on one coordinate, then we will have a large angle between the subspace. And any new task, for example, the A3 here, cannot improve this representation. So basically, we are considering this sequence of tasks where the first k task is just a unit vector ei in the i's coordinate, and the next tasks after k is the combination of the previous tasks. So like they are sharing the k-dimensional features. And we construct an adversary output of the algorithm where the arrow concentrates on one coordinate, for example, the k+1's coordinate. So there are actually 4 steps here. First, after learning the first k tasks, each with arrow epsilon_i, the angle between the learned feature subspace, which is the span of all of the features we have learned, and the underlying one, which is the true subspace, is at least omega of the square root of the sum of the square of epsilon_i. And for each new task allowed, the angle of the new task to the learned subspace is at least omega of square root of sum of I over epsilon I squared with high probability. So learning such a new task will not improve our representation. So this is similar to the simple case in 3 dimensions. And finally, we hope to solve all of the tasks up to arrow epsilon. So we need each epsilon I to be O epsilon over square root of k, and it leads to the lower bound of the sample complexity. And this also shows that our epsilon accuracy in our algorithm is also tight. We cannot use like a larger epsilon accuracy than ours. So finally, we can go beyond the linear features as I mentioned. So in our setting, for each label is labeled as sign of CI transpose sigma of W transpose X. And this sigma can be the nonlinear activation such as ReLU or sigmoid. So for our 2 algorithm, for the first one, the basic lifelong learning algorithm, we can learn k features instead of 1. Because it's nonlinear. And for the analysis part, we can consider the kernel of the features and regarding each feature as a potentially infinite dimensional vectors. So this will lead to the bound of the nonlinear ones has a factor of k higher than the linear one. And for the lifelong learning algorithm with representation refinement, so we do not have an efficient implement of our representation refinement step. So we can just using some heuristic methods like knowledge distillation to shrink the size of the feature while keeping it close to the learned ones. Finally, I will show the experiment results. So this is close to the empirical continual learning setting. So we consider the class incremental classification, where we learn new classes sequentially from C400. So we learn actually 10 classes each time, and so there are 10 tasks in total. And here we using an algorithm we propose named the heuristic lifelong learning algorithm. So we learn a separate encoder fi and the i's task, while the other encoders of fj, where j is smaller than I, are frozen during the training of the i's task. So our algorithm fine-tunes the last classifier layer using some memory buffers and the current task data. And our representation is the concatenance of all of the encoders we have learned. So this one is actually a little bit far from our theory because we do not have the step to check whether we need to learn a new encoder or not. So this representation grows with the number of the tasks instead of the number of the features. But as we can see, it can achieve a very good performance. So the red line is this heuristic lifelong learning algorithm, and it has shown the good accuracy compared to the other state-of-the-art algorithms. Also, if we plot the accuracy of the previous task to check whether it has tackled the catastrophic forgetting, so the performance is dropped stably and slowly. So I think it's totally fine here. Okay, so I think this is the end of the talk, and thank you very much. Do we have any questions, comments?
Thank you. Thank you so much for that. That was really wonderful, and I wish I was smart enough like you to understand 100% of everything you said. Yeah, I guess this is the time to, if anybody has questions, either online or if you were in MS Teams, feel free to just unmute your mic and chime in. Did I hear? Nope. So I can start with one. Um, I'm trying to remember. I guess how does this extend? I noticed that it works very well on this um, experiment you have up here. And my first question, I guess, is what's the parameter complexity? I guess for the heuristic algorithm that you've put here, like is a number of parameters growing higher or ends up higher or less than like the iCarl method, for example?
Yeah, I think like our model size is higher than the other results because like we grow the network size with the number of the tasks. So here it's not that obvious. It's not that much because we only have 10 classes, but like it would be a problem if we have more and more classes. So we think like one way to solve it is to using the knowledge distillation to shrink the size of the model while keeping it the same performance. But like we haven't yet implemented to see like how that will help with the performance. So, but I still think it's a feasible way to reduce the model size to make it probably more fair. Yeah.
That makes sense. But I mean, it's not like you beat the methods by 2% and you had a bigger model. Like the performance gains here in this plot are very significant. Um, do you have any other questions, either from online or in MS Teams? I saw you joined. You were on YouTube, Zaid, and you joined over here in MS Teams in the middle. Do you have any questions? Okay. So my next question is: are you still working on lifelong learning? Are you trying to expand some of the like foundations in your proofs to maybe more large scale, or are you pivoting away?
I mean, my ongoing project is not in lifelong learning, but it's also like learning features from unlabeled data, and it's more on theoretical side. So yeah, probably I will do more on lifelong learning in the future. Yeah.
Merge it, have a theoretical perspective on unsupervised, unlabeled lifelong learning in your next big thing.
Yeah,
Go
it's
ahead and
like
just
I'm not. It's like just in the initial step of learning directly from unlabeled data, and
right.
there's no lifelong part right now, but hopefully there will be in the future.
Awesome. Well, this work is truly outstanding, and I was the first time that I read your working paper, I was kind of, I guess, very uh, blown away by the. I guess I always considered a lot of this lifelong and continual learning. Most work seem to be only heuristical, and having this fundamental approach to it, I think, is very healthy for our community. So thank you very much for sharing it with us today. Um, and yes, I guess thank you everybody for joining on Teams or whoever's everyone watching on YouTube right now. You can catch us again next week at the same time, same place. And we will hear author Doliard talking about his Transformers work. Diatox Transformers for Continual Learning with Dynamic Token Expansion. We will see you all here next week. Thank you very much.